Skyscrapers look solid, massive, unmovable. They rise hundreds of meters into the air, made of steel and concrete, towering above everything around them. It's easy to assume they are rigid. They stand perfectly still. But that assumption is wrong. Skyscrapers move. In fact, they are designed to move. And if they didn't, they would be far more dangerous. Today we're going to explore why skyscrapers sway, how engineers control that movement, and why flexibility, not stiffness, is the real secret that keeps tall buildings from collapsing. As buildings grow taller, they face problems that short buildings never encounter. Wind becomes stronger at higher altitudes. Temperature changes are more extreme. Forces act over much larger distances. At ground level, wind might feel calm. But hundreds of meters above, it can be powerful and unpredictable. This creates pressure on the structure, and pressure creates force. As buildings grow taller, they face problems that short buildings never encounter. Wind becomes stronger at higher altitudes. Temperature changes are more extreme. Forces act over much larger distances. At ground level, wind might feel calm. But hundreds of meters above, it can be powerful and unpredictable. This creates pressure on the structure, and pressure creates force. Now here's the critical idea. If a skyscraper were completely rigid, that stress would have nowhere to go. It would concentrate in specific points, beams, joints, connections. And when stress concentrates, materials fail. Steel cracks, concrete fractures, bolts shear. Rigidity sounds strong, but in tall buildings, rigidity is dangerous. Instead of fighting movement, engineers allow it. When wind pushes on a skyscraper, the building bends slightly. Not enough to see from the ground, but enough to reduce force. This bending spreads stress over time and space. Instead of one violent push, the force becomes a gentle motion. Think of the difference between glass and rubber. Glass is rigid, it resists movement. Rubber bends, it absorbs energy. Skyscrapers behave much closer to rubber than glass. But how much do skyscrapers actually move? In very tall buildings, the top can sway by tens of centimeters, sometimes even more during storms. This movement is slow and controlled. You usually don't notice it unless you're near the top. And even then, it feels more like a gentle rocking than a shake. Movement alone, however, is not enough. Uncontrolled movement can be just as dangerous as rigidity. This brings us to one of the most fascinating tools in modern engineering: the tuned mass damper. A tuned mass damper is a massive weight placed inside a building, often near the top. It can weigh hundreds or even thousands of tons. At first, this sounds counterintuitive. Why add more weight to an already massive structure? The answer lies in physics. When a skyscraper sways in one direction, the tuned mass damper moves in the opposite direction. This opposing motion reduces the building's movement. Energy is transferred from the structure into the damper. Instead of amplifying vibrations, the system cancels them. The motion doesn't disappear. It becomes controlled. One of the most famous examples is Taipei 101. Inside this tower is a giant steel sphere. It is suspended like a pendulum. During strong winds or earthquakes, the sphere swings. As it moves, it stabilizes the entire building. People inside may feel motion, but the structure remains safe. This system works because of resonance. Every structure has a natural frequency. If external forces match that frequency, vibrations grow. This is what caused famous structural failures in the past. Tuned mass dampers are designed to counteract resonance. They tune the building away from dangerous frequencies. Wind is not the only threat skyscrapers face. Earthquakes create an entirely different challenge. Instead of gradual force, earthquakes introduce sudden acceleration. The ground moves rapidly. And according to physics, force equals mass times acceleration. When acceleration spikes, force skyrockets. If a building were rigid during an earthquake, it would experience enormous internal forces. These forces could exceed material limits in seconds. Instead of resisting earthquakes, skyscrapers are designed to absorb them. Modern skyscrapers use flexible joints, shock absorbers, base isolation systems. Some buildings sit on bearings that allow the ground to move independently from the structure. The building lags behind the ground motion. This delay reduces force. Once again, movement is the solution. Let's talk about materials. Concrete is excellent under compression. Steel is excellent under tension. But both materials have limits. Repeated stress can cause fatigue. Small cracks can grow over time. This is why skyscrapers are constantly monitored. Sensors measure movement. Engineers track vibration patterns. If something changes, it's investigated. Tall buildings are not static objects. They are living systems. Temperature also plays a role. Steel expands when heated. Concrete contracts when cooled. In a skyscraper, temperature differences between the sunny and shaded sides can be significant. If a building couldn't move, these expansions would create massive internal stress. So buildings are designed with expansion joints. They allow slow, controlled movement as temperatures change. Another often overlooked factor is human comfort. Even if a building is structurally safe, excessive motion can cause nausea. People are very sensitive to slow movement. Engineers design skyscrapers to limit acceleration felt by occupants. This is another reason tuned mass dampers exist. Not just for safety, but for comfort. So why don't skyscrapers collapse? Because engineers understand something crucial. Strength alone is not enough. Control matters more. Flexibility matters more. Predictability matters more. This philosophy represents a shift in engineering thinking. Early structures aimed to resist force at all costs. Modern structures aim to manage force. Instead of asking how do we stop movement, engineers ask how do we control it. Every skyscraper is a balance between strength and flexibility, between mass and motion, between resistance and absorption. This balance is carefully calculated, tested, simulated, refined. Before a skyscraper is ever built, engineers simulate years of wind, thousands of earthquake scenarios, extreme weather events, unexpected loads. The goal is not perfection, so the goal is survival. The next time you look up at a skyscraper, remember this. It is not standing still, it is gently swaying, adapting to forces you cannot see, absorbing energy, releasing stress. That movement is not a flaw. It is the reason the building is safe. Rigidity breaks. Flexibility survives. Skyscrapers don't stand because they are unmovable. They stand because they are intelligent. Designed to move. Designed to adapt. Designed to endure. If you enjoy learning how engineering and physics quietly protect us every day, subscribe to Engineer Explained. New videos every week, breaking down how the world works.